Hierbij open ik deze academische zitting, waarin Alexander van der Wiel het academisch proefschrift getiteld Overcoming Tumor Hypoxia, Factors Influencing the Efficacy of Hypoxia-activated Prodrug CP506, long title, in het openbaar te verdedigen. Mag ik u verzoeken een samenvatting te geven van uw proefschrift?
Geachte prorector, geachte leden van de corona, beste familie, vrienden en collega's. Dank jullie wel voor jullie aanwezigheid bij de publieke verdediging van mijn proefschrift getiteld Overcoming Tumor Hypoxia, Factors Influencing the Efficacy of the Hypoxia-activated Prodrug CP506. Ik vind de titel zelf net ook iets te lang, maar toch ga ik proberen om deze in het komende kwartier klaar en duidelijk uit te leggen. Kanker is een grote verzameling van heterogene ziektes en die worden alle gekarakteriseerd door een abnormale celgroei en ongecontroleerde celgroei. Uiteindelijk kan het leiden tot uitzaaiingen, dus dat de tumor op een andere plek in het lichaam verder groeit. Ongeacht de oorzaak is kanker een genetische ziekte, wat wil zeggen dat het veroorzaakt wordt door een opeenstapeling van schade aan het DNA, het erfelijke materiaal van de cel. Door bijvoorbeeld een herhaaldelijke blootstelling aan schadelijke stoffen, die je terugvindt in alcohol, sigarettenrook, maar ook in rood vlees bijvoorbeeld, verandert een gezonde cel zo langzaam in een kankercel, door een langzaam en meerstapsproces waarbij verschillende mutaties opeenstapelen. Het aantal gevallen van kanker, de incidentie en de prevalentie zal in de komende jaren jammer genoeg alleen maar stijgen. Ondanks de grote vooruitgang op vlak van kankertherapie en onderzoek is het dus absoluut noodzakelijk dat we meer precieze, meer gepersonaliseerde behandelingen vinden. Ondanks de grote variatie van tumoren die er bestaan, longkanker, borstkanker, colonkanker bijvoorbeeld, delen alle tumoren toch een bepaalde set van cruciale of essentiële kenmerken, waarvan hypoxie er één is. Hypoxie wordt gedefinieerd als gebieden met een laag zuurstofgehalte en dit komt in het gezonde lichaam normaal niet voor. In een tumor echter bestaat er een disbalans tussen zuurstofverbruik en aanlevering. Wanneer de tumor evolueert of groeit, krijg je zo bepaalde gebieden met een laag zuurstofgehalte. Dit is bijzonder slecht, omdat hypoxie een van de belangrijkste voorspellers is van een slechte prognose. Wat wil zeggen dat de patiënt met een hypoxische tumor minder kans heeft op een overleving dan een patiënt met een tumor die niet hypoxisch is. Dit komt omdat hypoxie bijdraagt aan de kwaadaardigheid of agressiviteit van een tumor en ook omdat het de efficiëntie of de werking van bepaalde therapieën teniet doet. Dit maakt hypoxie echter ook een van de meest interessante doelwitten om therapeutisch uit te buiten, omdat je 2 vliegen in 1 klap slaat. En verschillende manieren om dit te doen zijn reeds getest, waaronder het gebruik van hypoxie-geactiveerde prodrugs of HAPs. Dit zijn, zoals de naam al suggereert, geneesmiddelen die inactief zijn in normoxische gebieden, dus in het gezonde weefsel. Enkel in hypoxie, onder laag zuurstofgehalte, krijg je een activatie en zal uiteindelijk een cytotoxisch of een giftige stof gevormd worden die selectief kankercellen doodt. Verschillende HAPs zijn al geëvalueerd in het laboratorium met zeer veelbelovende resultaten. Echter, stuk voor stuk zijn ze teleurstellend gebleken in de kliniek eens ze getest werden op mensen. Wij denken dat dit komt doordat er een gebrekkige patiëntselectie op voorhand heeft plaatsgevonden. Je kan je voorstellen dat niet elke patiënt hetzelfde reageert op een hapbehandeling. Niet elke patiënt is hetzelfde. Sommige patiënten reageren bijvoorbeeld ook anders op een chemotherapie. Dat is bij HAPs net hetzelfde. Om dit meer concreet te maken, je kan je voorstellen gemakkelijk dat de patiënt met tumorhypoxie, dus met activatie mogelijk, beter gaat reageren op een hap dan een patiënt die geen tumorhypoxie heeft. Wij geloven dus nog altijd in het concept van HAPs maar alleen als de correcte groep van patiënten op voorhand geselecteerd wordt. Daarom hebben wij CP506 ontwikkeld, een nieuwe en verbeterde hypoxie-geactiveerde prodrug met gunstige eigenschappen. Om CP506 succesvol in de kliniek te laten toepassen, moeten wij dus ook op voorhand correcte patiëntselectie kunnen doen. Om dit te kunnen doen, moeten wij weten welke factoren de effecten van de behandeling van CP506 beïnvloeden. En daarvoor moeten we kijken naar de chemische structuurformule of hoe CP506 precies geactiveerd wordt. Linksonder in beeld zie je de structuurformule of chemische formule van CP506. Eens in het lichaam wordt het omgezet tot een zuurstofgevoelig intermediair of een tussenvorm. Als er zuurstof aanwezig is, reageert dit onmiddellijk terug naar de inactieve prodrug. Enkel in gebieden met een laag genoeg zuurstofgehalte krijg je een verdere omzetting naar het geactiveerde metaboliet, de giftige stof. Dus alleen in hypoxische gebieden, die je alleen in de tumor vindt, wordt dit medicijn geactiveerd. Als we kijken naar welke factoren nu, op basis van dit schema, wij kunnen identificeren die een rol hebben in het bepalen van de behandeling van CP506, dan kunnen wij ten eerste al de mate van hypoxie logischerwijs identificeren. Hoe meer hypoxisch een tumor is, hoe groter ook de activatiezone voor ons medicijn gaat zijn, hoe meer uiteindelijk ook de omzetting je gaat hebben naar het geactiveerde metaboliet. Ten tweede heb je ook de gevoeligheid, de intrinsieke gevoeligheid van een cel voor het metaboliet. Dus eens dat het metaboliet geactiveerd is, hoe gevoelig is een tumor of een cel voor de werking van dit medicijn? In mijn proefschrift heb ik gekeken naar welke factoren dus van invloed zijn op de werking van CP506. Hypoxie is een eerste verband en is intuïtief ook logisch dat dit natuurlijk de werking van CP506 gaat beïnvloeden. Opnieuw, hoe meer hypoxisch de tumor is, hoe groter de activatiezone gaat zijn voor hypoxie-geactiveerde prodrug en naar waarschijnlijkheid ook hoe groter het effect kan zijn. Toch mogen we in de wetenschap niet uitgaan van een intuïtief verband en moet dit getest worden in zowel proefbuisjes als proefdieren. Het voordeel van proefbuisjes is dat we hier experimenten kunnen doen met cellen in sterk gecontroleerde condities. Zo hebben we bijvoorbeeld cellen gekweekt onder normoxische omstandigheden, normoxie, en dat is eigenlijk gewoon de lucht die wij inademen, dus 21% zuurstof. We hebben eveneens cellen gekweekt onder hypoxische condities, daar is geen zuurstof aanwezig. Vervolgens hebben we ons medicijn toegediend, CP506, en we hebben gekeken welke cellen sterven en ook welke cellen misschien blijven leven. Hier zie je zo'n overlevingscurve van cellen onder normoxische condities. Ons medicijn zou in principe niet mogen werken. We zien dat bij een zeer hoge concentratie van CP506 aan de rechterkant we een kleine afname hebben van het levende aantal cellen. Dus een kleine celsterfte vindt plaats. Onder hypoxische condities echter zien we dat deze afname veel sterker is. Je ziet bij lagere concentraties dat eigenlijk volledige celdood plaatsvindt. We hebben geconcludeerd dat CP506 tot ongeveer 200 keer beter werkt in hypoxische cellen vergeleken met normoxische cellen. Dit is gevalideerd in 50 verschillende cellijnen. Echter moeten we ook altijd onderzoek doen in proefdieren. De tumor en de patiënt is iets complex dat wij onmogelijk kunnen nabootsen in het lab. We hebben daarom muizen die we geïnjecteerd hebben met tumorcellen. Deze tumorcellen groeien uit tot een tumor en die kunnen we feitelijk behandelen als de tumor van een patiënt. We kunnen die behandelen, maar we kunnen ook meten hoe groot de respons is, of een tumor groeit of krimpt. Nadat we of voor we CP506 toegediend hebben, en om dus eigenlijk de relatie te onderzoeken tussen tumoroxygenatie, dus de mate van hypoxie aanwezig, en het effect van de behandeling, hebben we deze dieren eerst blootgesteld aan verschillende zuurstofconcentraties die zij moesten inademen. 21% zuurstof is opnieuw de controleconditie, de lucht die wij inademen. We hebben ze ook blootgesteld aan 7% zuurstof, dus 3 keer lager het aantal zuurstof dat we inademen. Het bloed zal dus ook minder goed zuurstof kunnen opnemen. De tumor zal ook minder zuurstof bevatten en er zal ook meer hypoxie aanwezig zijn. Naar verwachting zal het effect van onze hap dus groter zijn. Voor 95% zuurstof geldt net het omgekeerde. Er is veel zuurstof aanwezig in de lucht die we inademen, veel zuurstof in het bloed, meer in de tumor en dus ook minder hypoxie. Ons geneesmiddel zou in theorie minder goed moeten werken. Hier zie je een voorbeeld van een tumorgroeicurve. Je ziet dat de dieren of dat de tumoren snel groeien zonder enige behandeling. De dieren sterven dan ook snel door een te grote tumorlast. Als we ons medicijn toedienen bij 21% zuurstof, zien wij dat de tumorgroeicurve aanzienlijk vertraagd is. Het medicijn heeft een sterk effect. Onder 95% zuurstof, dan is er meer zuurstof aanwezig, meer zuurstof in de tumor, dus minder hypoxie, verwachten wij een minder groot effect. En dan verwachten we ook dat die curve naar links, naar de controlecurve toe gaat schuiven. Dat is ook wat we zien. Voor 7% verwachten we net een sterker effect. De curve moet dus meer uitgesproken naar rechts gaan. En dat is ook wat we zien. Belangrijk hier is dat we aantonen dat er een kausaal verband bestaat tussen de mate van tumorhypoxie en de effecten van CP506. Met andere woorden, hoe meer hypoxisch een tumor is, hoe groter ook het effect zal zijn van ons geneesmiddel. Dit hebben we ook gevalideerd in in totaal 14 andere diermodellen. Die laten stuk voor stuk zien inderdaad dat er een verband is tussen hypoxie en de effecten van CP506, maar die laten ook zien dat er meer factoren een rol kunnen spelen. En dat brengt mij naar de tweede factor die we gaan bespreken vandaag. Dat is de intrinsieke gevoeligheid van een cel of van een tumor voor CP506. Om te kijken wat de intrinsieke gevoeligheid van een cel bepaalt voor ons geneesmiddel, moeten we kijken naar hoe CP506 precies werkt. CP506 werkt door het DNA te beschadigen van kankercellen. Door het DNA te beschadigen kunnen deze cellen niet meer verder delen en moeten ze uiteindelijk sterven. Zo krijg je dus een tumorcontrole. De schade moet met andere woorden hersteld worden voor de kankercel om te overleven en ook voor de kanker om verder te kunnen groeien. Gelukkig heeft ongelukkig in het geval van kanker de cel een arsenaal aan eiwitten ontwikkeld die deze DNA-schade kunnen herkennen, selectief kunnen wegknippen en dan ook kunnen vervangen door een gezond stukje DNA. Als deze reactie goed werkt, kan de cel dus DNA gemakkelijk herstellen en dus verder delen. Voorbeelden van dergelijke eiwitten zijn bijvoorbeeld BRCA2-eiwitten, bekend misschien van borstkanker. Echter werken in sommige tumoren deze eiwitten niet, met als resultaat dat zij de DNA-schade geïnduceerd door CP506 niet kunnen herstellen. Wij vroegen ons af of deze tumoren ook daadwerkelijk gevoeliger zijn voor CP506. We hebben daarvoor cellen gepakt met een functioneel BRCA2-eiwit, hier in het groen. De BRCA2-eiwit werkt en kan DNA-schade herstellen. We Met een speciale techniek zijn we erin geslaagd om dit eiwit eruit te knippen, zodat in de ongezonde cel hier rechts en in het rood aanwezig er geen BRCA2 aanwezig is. Deze cel kan theoretisch gezien de DNA-schade geïnduceerd door CP506 ook niet herstellen. We hebben na behandeling gekeken opnieuw in proefbuisjes en proefdieren wat de respons op ons medicijn gaat zijn. In proefbuisjes hebben we gekeken naar DNA-schade. Dus hier zie je een foto van cellen in het blauw. Als er DNA-schade is, kleuren deze cellen groen. In cellen met een functioneel BRCA2-eiwit zie je een klein beetje DNA-schade, misschien in de cel aan de linkerkant in het midden in het beeld. Als er geen functioneel BRCA2-eiwit aanwezig is, wat dus niet deze DNA-schade kan herstellen, dan zien we dat deze DNA-schade in het groen veel meer uitgesproken aanwezig is. We hebben geconcludeerd op basis van dit en andere experimenten dat CP506 DNA-schade induceert, of op een grote manier induceert in cellen zonder BRCA2 en dat deze schade ook langer onhersteld blijft. Opnieuw moeten we dit natuurlijk ook in proefdieren valideren. Hier zie je opnieuw de controle van proefdieren. Zonder behandeling zie je dat de tumor snel groeit en dat de dieren snel sterven door een te grote tumorlast. De controle met functioneel BRCA2, hier zie je dat CP506 een relatief klein, maar toch nog steeds een significant effect heeft. Het werkt nog altijd in tegen tumorgroei. Als BRCA2 niet aanwezig is, dan zien we dat dit effect veel groter is. Dit hebben we eveneens gevalideerd in andere cellijnen. We kunnen concluderen dat tumoren zonder BRCA2 en zonder andere DNA-hersteleiwitten tot 3 keer gevoeliger zijn voor ons medicijn CP506. Echter, wat gebeurt er nadat CP506 zijn werk gedaan heeft? Wat als er geen hypoxie meer is? CP506 elimineert namelijk de hypoxische gebieden. Dit hebben we ook aangetoond. Dus na een paar behandelingen heb je geen hypoxie meer aanwezig en zal ons medicijn ook niet meer werken. De non-moxische cellen die je hier ziet, die kunnen natuurlijk echter ook opnieuw uitgroeien tot een nieuwe tumor. En die moeten ook aangepakt worden, willen wij kanker kunnen genezen of beter onder controle kunnen houden. Het idee is dus om CP506 te combineren met therapieën die deze non-moxische cellen gaan aanvallen. En dan brengt me terug bij het begin. Hypoxie is een negatieve factor voor de effecten van chemotherapie en bestraling. Die werken niet of veel minder goed op hypoxische cellen. CP506 aan de andere kant werkt niet op non-moxische cellen. Dus door deze twee therapiemogelijkheden te combineren, bestraling, chemotherapie, verwachten wij dus dat de tumor op 2 fronten aangevallen wordt en verwachten wij dus dat de efficiëntie van beide therapieën de hoogte ingaat. Hier zie je een curve waarin de tumoren alleen bestraald zijn, met op de y-as het percentage van de patiënten, of in dit geval muizen, met een tumorcontrole. Wat wil zeggen dat de tumoren niet meer groter worden. Na een bestraling met een bepaalde dosis zien we dat 30% van deze tumoren onder controle blijft. De overige 70% is te veel gegroeid. Als wij CP506 toedienen voor behandeling, dus waarin hypoxische gebieden geëlimineerd worden, dan zien we dat dit aanzienlijk hoger wordt. We hebben nu een tumorcontrole van 60% in vergelijking met 30%. CP506 verbetert dus ook de efficiëntie van bestraling en ook van andere therapieën die niet werken in hypoxische gebieden. In conclusie. Hypoxie is een belangrijke eigenschap van tumoren en draagt bij tot de kwaadaardigheid en ook resistentie tegen conventionele therapieën. CP506 is een nieuwe hap met gunstige eigenschappen. En patiëntselectie is absoluut cruciaal voor een succesvolle klinische implementatie van HAPs en dus ook van CP506. We hebben in het proefschrift aangetoond dat hypoxie en de DNA-herstelstatus de respons van tumoren en cellen op CP506 sterk kunnen voorspellen. We hebben ook aangetoond in hoofdstuk 6 en 7 dat een hap, een CP506, pas optimaal benut wordt in combinatie met andere therapieën zoals chemotherapie en bestraling. En tot slot, op basis van bevindingen in het proefschrift wordt CP506 dit jaar hopelijk op mensen getest voor het eerst. En we zullen dit geneesmiddel ook op patiënten gaan selecteren op basis van hypoxie en ook op basis van de DNA-herstelstatus. Bij deze dank ik jullie voor de aandacht en geef ik graag het woord terug aan de prorector.
Hartelijk dank voor deze heldere voordracht waar enorm veel informatie voorbij is gekomen. De oppositie zal in het Engels plaatsvinden. And the opposition will be opened by Professor van Engeland, Professor of Pathobiology of Cancer, especially the role of epigenetics at this university. Professor van Engeland was also chair of the assessment committee and is secretaries of the assessment committee.
Thank you, Mr. Prorector. Dear candidate, first of all, congratulations with this beautiful thesis. It's innovative, and I think it's also an honest evaluation of the state of the field, which I truly enjoyed. So, regarding the state of the field, you mentioned that tumor hypoxia has been considered a promising therapeutic target for decades, but it's still not being used in the clinic. And you mentioned a few reasons, but what do you think is the main reason why there's no implementation?
The main reason that there is no highly esteemed opponent, thank you for your nice first question. I think the main reason why no hypoxia-targeted strategy in terms of hypoxia-activated prodrugs at least is implemented is because, again, not this correct amount of patient selection or stratification has been taking place. So a lot of research is actually being performed, and a lot of hypoxia-activated prodrugs have already been evaluated in the clinic with highly promising preclinical findings and also highly promising, let's say, phase 1, phase 2, and perhaps even phase 3 clinical trials. But they ultimately all failed, and that is, I think, due to a lack of patient stratification of these HAPs. So that's why we want to include, for at least the upcoming phases of, if CP506 progresses to this, of clinical trials, we want to include a biomarker-based approach to select the correct group of patients that are expected to benefit most from our hypoxia-activated prodrug treatment.
So if that would be the main reason, why then don't we go back and study these trials retrospectively with the proposed biomarker, and then we can see whether that's the true reason?
Yeah, absolutely. And I think for a hypoxia-activated prodrug, tirapazamine, that has been done in the past. So retrospectively, a group looked back at, for example, the hypoxia status as assessed by hypoxia PET imaging, using, I think, F-MISO as a PET tracer. And there they did see a correlation between responders to tirapazamine and the non-responders. So hypoxic tumors, as defined by PET positivity, so a PET marker that is activated in hypoxic regions as well. These patients were responded retrospectively better to the tirapazamine. For other trials, I do not think that this has been included. For example, monitoring hypoxia before treatment. So that is, of course, a limitation. And I think that it is not possible always to look back if the patients were indeed hypoxic, yes or no.
Okay, so looking into the future then, should we design the prospective trials more efficiently, with also collecting material in order to, in case we need to, go back retrospectively and try to explain the results of the trial?
Yes, that would be really an ideal situation. Yeah, that you collect the materials, as long as, of course, it's not an extra burden for the patient or too much of a burden, that we can retrospectively, in case that we miss something, can look back at different factors to see whether or not this might also affect the treatment response. Yeah. I think the optimization or design of clinical trials should be really done on a biomarker-based approach, because not only can you reduce or increase the power of your study, you need less patients, and a drug can, of course, progress to the market also more quickly if this is done correctly. So in an ideal world, you would know beforehand, of course, which markers that you would need to include. And for CP506 and HAPs, I think that is at least in part clear. But also just in case, if it is not too much of a problem, of course, or infeasibility, that you want to include other materials that we can analyze later on for retrospective analysis in case that we missed something.
All right. I don't completely agree that lack of stratification is the main explanation, because I see a lot of similarities with my own field, cancer biomarker identification. And in that field, less than 1% of biomarkers actually will make it to the clinic. Less than 1%.
Yeah.
So, and there's multiple reasons for that, but one of the main reasons is methodology, research methodology. So we are producing a lot of research waste just because the studies have not been designed properly. And I think that's also going on in this field. What is your opinion on that?
Yeah, that is absolutely the case. Yeah. Also, for example, for CP506, let's say that we want to implement a biomarker that is assessing tumor hypoxia. Which biomarker do we then select? For example, referring in chapter 3, we see that CP506 is becoming activated at oxygen concentrations below 0.1% oxygen. If you want to include a biomarker that is, for example, let's say pymenidazole or hypoxia PET imaging, these PET traces are activated at oxygen concentrations at 1 to 3% oxygen. That might also not be the best biomarker-based approach. So I think that in that case, we need to treat carefully and select biomarkers that prove or have proven to be useful in this regard. Yeah.
And then
opt for use that in the clinic, if ideal, if possible. Yeah.
So what often happens is that there's one study that has a beautiful result, which make the headlines of the journals and the newspapers. And then the second study, the effect is a little bit less. We call that regression to the mean phenomenon, right? So if you validate specific findings multiple times, then the effect mostly disappears or reduces, except for the findings that are real findings and are not chance findings.
Yeah.
So how should we accommodate that knowledge in new studies?
In new studies, well, it's always, you never know for sure, of course, which is a true finding, let's say, and which not. So I think if we incorporate better, more preclinical evidence that is truly showing that a biomarker can be used in the clinic, and if we can also ensure that across multiple centers this is done exactly in the same way, because a lack of standardization across that is also a major problem, then we can try to reduce that. I do think that it is inherent in this research, and that it's very difficult to overcome this.
Well, then we have to perform super boring validation studies multiple times, but that's not really interesting for most scientists, right?
No,
I think that's the only way to find out if this is a real effect.
I think beforehand just identifying the biomarkers that are true biomarkers of response. I think it's just let's say a gamble that you have to take sometimes. And validation studies, of course, are not very interesting, but maybe beforehand we can do a more validation study of a certain biomarker of response, publish that, and make sure that, again, this standardized way is incorporated in every trial that follows the first one.
Okay. Do I have time for one more question? Yeah? Okay. So I would like to go to chapter 5. In which you study the effect of HR deficiency. And you mentioned that this occurs in about 70% of cancer patients.
17, yes.
Yeah. 17?
Yeah.
Yeah. So what would be the percentage of patients if we also have to include hypoxia?
If you also have to include hypoxia, so hypoxic tumors, approximately 60%, 50 to 60% of hypoxic tumors, or solid tumors, are hypoxic. Of all tumors, an estimation of 17.4% is showing signs of homologous recombination deficiency. If you combine that, then 10% would fall under both categories, so being both hypoxic and homologous recombination deficient.
Okay, and so you were only discussing hypoxia as a prognostic factor in cancer. But there's multiple profiles that have been published to be prognostic. So some of them will overlap with hypoxia as a biomarker, some won't. So do you think that just measuring hypoxia would be sufficient to identify that part of patients that needs to be treated more aggressively than other patients?
I think that the part of patients that are hypoxic should be treated with an hypoxia-activated prodrug. Is hypoxia sufficient for that? It might be, yeah, we will see. In our studies, we show that we can predict the tumoral response of CP506 based on the degree of tumor hypoxia. We just see that if the homologous recombination deficiency is also present, the effect is much, much more. Again, CP506 is likely not going to be given as a monotherapy. It can be as an aid to reduce the amount of hypoxia present to allow better or other not hypoxia targeted, but therapies targeting normoxic cells. So I think, not as a monotherapy, it will not succeed, but in combination with other treatment modalities.
Okay, thank you for your answers, and I'll return the word to the prorector.
Thank you very much. And now, good morning, Canada, as we will move over all the way to Canada for the next opponent, Professor Wouters, Professor of Medical Physics and Radiation Oncology at the University of Toronto. He was also a member of the assessment committee. Professor Wouters.
Yes, thank you, Prorector. And just as I start, I want to offer my congratulations to the candidate and to the promoter committee for producing a very nice thesis, which I enjoyed very much to read. What I'd like to do is to ask you, first of all, about some of the details and the findings that are reported in Chapter 4, where you've investigated the impact of specific DNA repair proteins and pathways on the sensitivity to CP506 and also the hypoxic cytotoxic ratio. And in particular, I was intrigued by the finding that you report in one of the cell lines where you have used a cell line deficient in non-homologous end joining. And you report that these cells demonstrate less toxicity to CP506, despite the fact that these cells harbor a very substantial DNA repair defect. So I was wondering if you could just elaborate a little bit on this result, and also your interpretation as to what might be the underlying reason why those cells deficient in DNA repair are actually more resistant to the drug.
I would like to thank you for your kind words and your interesting question. So indeed, we included the DNA PKCS knockout, so that's an important protein in the non-homologous end joining pathway, to also study the effects of a deficiency on the efficacy of CP506. And non-homologous end joining is involved in the repair of double-stranded DNA breaks. It does so in a, well, not error-free way, in contrast to, for example, homologous recombination, which uses the homologous sequences to correctly repair, or almost correctly repair most of the time, the DNA damage. So non-homologous end joining does so in a less precise manner. So my speculations are that since non-homologous end joining is active mostly throughout the cell cycle, especially, for example, in the G1 phase of the cell cycle, whilst homologous recombination repair is mostly restricted to the G2 and S phase of the cell cycle, it is as that if, for example, non-homologous end joining, is not present, then I think that the homologous recombination part can perhaps take over, or other DNA repair mechanisms can take over to repair the CP506-induced DNA damage, in this case in a more precise way, leading to less toxicity because the cell damage or the DNA damage is properly repaired. While for non-homologous end joining, this is not the case, leading to errors, and an accumulation of these errors will ultimately result in premature cell death. And we do see that in both the cell viability assays, as in the clonogenic cell survival assays, 3D spheroid assays, and in vivo as well, that actually a deficiency in non-homologous end joining offers a protective effect to the effects of CP506.
And how do you interpret it with respect to the fact that you've measured phosphorylation of H2AX, which is known to mark sites of double-strand breaks throughout the cell? You see very, very widespread phosphorylation, and at very high levels, up to 72 hours after treatment with the drug. And yet, again, the cells that have a defect in repair of those are more resistant to the drug. So what do you think this means about what you're measuring with gamma H2AX?
First of all, gamma H2AX is of course a marker of double-stranded DNA breaks. CP506 as a bifunctional alkylating agent results in interstrand crosslinks that can then, for example, reduce or result in double-stranded DNA breaks. So if I'm going to be honest, gamma H2AX is not the ideal marker to measure DNA damage induced by CP506. We should go or look for different assays that more directly look into the interstrand crosslinks. For example, an alkylite comet assay might be an option here, or also to look into different markers of DNA damage. For example, more functional ones like RAD51 foci induction might also be an option right here. So gamma H2AX is not the best marker for this type of DNA damage. We do see very interesting results, in my opinion, in figure 3 of chapter 4. And there you can see indeed that you have an increasing induction of gamma H2AX foci up to 72 hours, and we did not test later, but perhaps even longer than that, you do see an induction of gamma H2AX. That is not in line with other drugs or DNA damaging compounds. For example, radiation, you have a peak induction of gamma H2AX at 6 hours, which will then reduce the baseline relatively shortly after. Other alkylating agents have a peak at, let's say, 24 hours that slowly decrease. So this is not in line with these findings. So not only is gamma H2AX not the best marker for this type of DNA damage, in this case it also produces perhaps strange results. We tried to explain that a little bit in the discussion of chapter 4, and it might be that, for example, CP506 induces apoptosis, and apoptosis is also a known regulator that can upregulate phosphorylated histone 2AX in a non-specific or not DNA damage related manner. And I think that is going on here. So for upcoming experiments, I would focus on readouts or experiments that focus on the truly identification of the interstrand crosslinks being induced, and also perhaps include other assays that assess the functionality of the homologous recombination pathway instead of this type of DNA damage being induced.
Yeah, I think that's I agree with your interpretation there. I think you're essentially measuring another assay for cell killing or cell death or cell response in that way, as opposed to a DNA damage response in some kind. Okay, just in the last minute, I wanted to just ask you also about something a bit more general. That, you know, you've put together a large parts in this thesis about areas that control sensitivity to the drug. And if you were asked to design a clinical trial for testing this agent, can you just give me a little bit of the parameters of that trial? What would your trial look like in terms of dosing or combination, and what would the entry criteria be for the trial?
The entry criteria of the trial, so first of all, we need to test, of course, toxicity in humans. That will be done in an upcoming phase 1 clinical trial, and also the optimal dose in the clinic will be determined. So looking at trials that, if successful, are continuous of that, I would include... Sorry,
I mean more around patient selection.
Yeah.
Who would be included in the trial?
Well, basically any patient with a tumor that is proven to be hypoxic and ideally also shows characteristics of homologous recombination deficiency. And that can, for example, be done by the techniques described in Chapter 5. So, for example, the classifier of homologous recombination deficiency, the CORD algorithm, that can be included to predict whether or not a patient is hypoxic. Ideally, we want to include both, so both the patient that is hypoxic and has characteristics of a homologous recombination deficiency, as these patients are expected to benefit the most from treatment with our drug.
Okay, thank you. I'm satisfied with the answers, and I'll turn it back to the pro-rector.
Thank you, Professor Wouters. We move now to the other side of the world, as Professor Prushi is in India. So good evening. He will continue the opposition. Professor Prushi is Professor of Applied Radiobiology at the Department of Radiation Oncology of the University of Zurich. So please, Professor Prushi.
So, dear Prorector, thanks a lot for giving me the word. And I would like to congratulate also to the candidate. I also very much enjoyed reading your thesis. I would like to move a little bit ahead towards Chapter 6, where you combine the compound with ionizing radiation on the preclinical level. And I actually wonder, when you move ahead towards also to the clinics, how would you combine it? Would you combine it in a neoadjuvant way, in a concomitant way, or in an adjuvant way, your compound, independent of any kind of biomarker? Let's say you are biomarker positive and HR also fits your specificities. How would you combine it? Do you think maybe such kind of time regulations are more important?
Highly esteemed opponent, thank you for your kind words and question. If I understand the question correctly, it is the timing about how we would combine CP506 with radiation or basically any other therapy.
No, let's go with radiation.
Yes, so radiation, of course, hypoxia is a known factor to induce radioresistance. So hypoxic cells are 2 to 3-fold more sensitive to radiotherapy. So ideally, we would remove all the tumor hypoxia before we would administer, with CP506, before we would administer or treat patients with radiotherapy. So first, I would give CP506. Until the hypoxic cells ideally are disappeared or have dissolved, and then with radiotherapy to enhance the response of the tumor to radiotherapy. So first CP506 and then afterwards radiotherapy, ideally. Yes, in the clinic, of course, we tend to fractionate radiotherapy, so not give one dose but multiple doses over a certain amount of time. And I think in that light, it is more important to move towards a more hypofractionated radiotherapy because there you have less effects of the reoxygenation. So that means that if you have the reoxygenation, for example, after radiotherapy, you will have less hypoxic areas for CP506 to work in. With the hypofractionation, this is less the case, so CP506 still has added value to this treatment scheme. So, in short, CP506 before radiotherapy, and preferably in a hypofractionated scheme if done in multiple doses.
But do you think that all tumors can be treated with hypofractionation? I mean, does hypoxia also depend on tumor size?
Tumor hypoxia does not necessarily respond to tumor size. You have very small tumors, let's say from 1 millimeter, that are already hypoxic. So I do not think that that is the main reason why tumors are hypoxic. I think that certain tumor types tend to be less hypoxic than others. And again, to that, I would try to find a way to image before treatment how hypoxic a tumor truly is. So,
but interestingly, we know that in response to fractionated radiotherapy, we indeed see reoxygenation. But with hypofractionated treatment, or even with single stereotactic body radiotherapy, it is known that even hypoxia might increase during therapy due to the radiation. So maybe this is an argument to use your compound after radiotherapy.
Yes, that's also the case. That's also something that we investigated. So we investigated, that is not published and not included in this thesis, what timing would be ideal. So giving CP506 before radiation, when there is tumor hypoxia present, that will be eliminated, and then giving radiotherapy, or giving CP506 immediately after radiotherapy, when there is a small increase or an increase in hypoxic tumors. Yeah. I think that the main conclusion of these findings was that giving CP506 before radiation was the best way to move ahead.
But do you have also preclinical data on that?
Yes.
Okay, so now let me end with a more general question. Well, you try to exploit tumor hypoxia, but why at all exploiting tumor hypoxia? Why not increasing the PO2 at all? Maybe this is the much better approach.
Sorry, could you repeat your question? To increase the oxygenation of the tumor?
I mean, what you are doing, you try to exploit tumor hypoxia with your compound. Otherwise, it would not be activated. It's a prodrug. And then at the same time, you will target also these hypoxic tumor cells. But maybe one should, in general, not try to exploit tumor hypoxia, but rather to increase the PO2 in the tumor and try to reduce tumor hypoxia before radiotherapy.
Yes, several studies have actually also tried to explore that by, for example, using vasodilators before or giving before radiotherapy. So even the principle is very interesting. I believe that these clinical trials failed or stopped because they did not show efficacy in this case. Yeah, but those are approaches that are being used. Using hypoxia-activated prodrugs is, of course, not the only way to target or exploit tumor hypoxia. You have, for example, strategies that act as oxygen mimetics that function in a similar fashion as oxygen that can reduce or fixate, let's say, DNA damage induced by ionizing radiation. You also have strategies to increase the tumor oxygenation by a combination of vasodilation with, for example, breathing of hyperbaric oxygen. Those are all strategies that have been tested before. Yet they showed interesting preclinical data. I believe that in later phases, they failed to show efficacy, even though the principle is interesting.
So you would say you do not know at this stage whether your approach will be the better one in the clinics?
Well, we will not know that until we try it, I guess.
Okay, thanks a lot.
Well, thank you, Professor Pruschi. And the opposition will be continued by Dr. Ruschop. He is Associate Professor of Radiotherapy at this university, so we're back to the Netherlands. He was also a member of the assessment committee. Dr. Ruschop.
Thank you, Mr. Pro-Rector. Well, dear candidate, first of all, I would really like to congratulate you with this piece of work. It's a very nice, coherent piece surrounding CP506, and obviously I would also like to extend these congratulations to the promotion committee. So several questions already that I was going to ask you were already answered, but no worries, I still have ample munition to shoot with. So, and one question was actually triggered by my fellow opponent. So you claim that most trials have failed due to the lack of stratification. So then why design a new hub instead of just using TH302 and do proper patient stratification?
Esteemed opponent, thank you for your kind words. Any question? I do agree that ifosfamide or TH302 is actually still a promising candidate and will likely have or could have some use in the clinic. But I also do believe that our drug is better because we did not, of course, compare it directly to each other. So CP506 versus TH302. A first major advantage of CP506 is that it is characterized by a very low KO2 value, which means that it is becoming, or that half of the prodrug is being activated at very low oxygen concentrations.
So is that always an advantage? Because so obviously there are lots of degrees of hypoxia in cancers. And so how do you know exactly that you're targeting the correct cells? Because usually people think that the anoxic cells are towards the necrotic region, which does not appear to contribute much to regrowth of cancer.
So it is being activated in the truly hypoxic cells, or the anoxic cells maybe close to, so at oxygen levels below 0.1%. But the advantage of CP506 is that it is also characterized by a high bystander effect, meaning that once inside the activation zone, so the truly hypoxic or close to anoxic zones, the activated metabolites can diffuse out of this activation zone and can also target adjacent cells that are more oxygenated, so at higher oxygen levels, but oxygen levels that are still conferring resistance to radiotherapy and chemotherapy. So you have this truly hypoxic activation zone. Also, this ensures that it is not activated in slightly hypoxic tissues, like the liver and the bone marrow, for example, to try to reduce the toxicity. Other HAPs, by the way, have this toxicity sometimes as well, such as tirapazamine. So it gets activated in the truly hypoxic zones, but its bystander effect allows it to also target the more adjacent cells. So it targets the relevant cell group.
Okay, thank you. So coming back to the tissues that you just mentioned, so there is some physiological hypoxia in normal body. And you're including patients in your trial with any type of cancer, including most likely lung cancer. So the advanced stages of lung cancer, the drop in PO2, would that cause any issues? Would you expect any issues in activation of prodrugs in these, at current situation, mild hypoxic regions, which might drop in oxygen pressure as well?
Yeah. I think studies have shown that even a drop in PO2, that after a certain amount of time, the oxygen levels in the tissues, the healthy tissue itself, will stabilize to normal levels. So even while these tissues might be then slightly less oxygenated than normal in healthy conditions, it is still not low enough to allow activation of CP506. So even in these end-stage diseases, you would only get activation in the truly hypoxic or almost anoxic regions of the tumor that can still only be found within the tumor.
Okay. Well, thanks. So if I can then ask a few specific questions on chapter 7, for example. So here you address the immune responses and how CP506 could contribute to better response to the tumor. And in figure 2, you measure cell death, basically, and you measure calreticulin 1 expression, HMGB1 release. And these, well, in my profession, they trigger some specific interest because these are processed in a non-canonical way or in autophagy-mediated secretory pathway. So, and my question is basically, so how do you know this is immunogenic cell death? Because you're measuring more apoptosis. HMGB1 can also be secreted just because the cell needs to get rid of it, and calreticulin can also be expressed because the cell is detaching or doing something else. So how did you measure this?
How do you measure this? Well, of course, these are markers that can indeed point to immunogenic cell death, but they're not always indeed specific. So ideally, we would measure this in a different assay, for example, that we take off the medium of cells, so the HMGB1 is a secreted factor, or that we co-culture, for example, the cells that have been treated with CP506 that have shown an increase in HMGB1 and shown a translocation of calreticulin with immune cells, for example, and that can then be checked if this is an immunogenic cell death or not.
Did you do this? Because I couldn't find it in the chapter.
No, we did not do this.
You did it in the spheroid, comparable assay in the spheroids,
yeah,
but there you had the CP506 and also the splenocytes that appear to have, let's say, additive effects. And if I would expect a proper activation of the immune system, you would expect a little bit more, I think, than additive. So, yeah, how would you interpret these results if they wouldn't Yeah. I'm a little bit more skeptic about the activation of the immunogenic cell death in this case. So perhaps we can discuss this a little bit later on as well.
That's also
and
possible,
I'll give
yes.
back the word to the co-rector.
Well, I was nearly getting worried, but thank you very much for your opposition. And the opposition will now be continued by Dr. Menegakis. He is postdoc tumor biology at the Netherlands Cancer Institute. So please, Dr. Menegakis.
Thank you very much, dear Prorector. Dear candidate, also accept my congratulations for your work and to the committee as well. I think it is a very impressive amount of work and covers from the chemistry of the drug up to a lot of different aspects of biology from 2D, 3D, and tumor. But as you know, usually in research we try to answer one question and 3 more are open. So I would like to ask you, and in some more specific aspects that some of the previous opponents are actually touched, but a little bit to challenge you more. So I would like to go back to the chapter 4, where you see the HR deficiency to actually be a very prominent effect, giving very prominent effect in CP. And to me, this is a bifunctional alkylating agent, so it will cause interstrand crosslinks. And that, to me, will mean that in the replication fork we'll have terrible problems to deal with that will turn into probably double-strand breaks in S phase. And that's why probably Fanconi anemia and HR factors are so critical to deal with this damage. But I have an issue, because the DNA repair is actually very much skewed based on the cell cycle. So I see that you did these experiments with putting the cells for 4 hours in anoxia, and that is probably critical for the activation and the metabolic action of the drug. But what is happening in the cells that are really in very low oxygen? Because to my feeling, most of the cases, the cells are actually not cycling. So would that be killed?
Esteemed opponent, thank you for your kind words and also your challenging question. Yeah, indeed, it's true. So under anoxia, the cells stay stuck into the cell cycle. And alkylating agents and chemotherapeutics actually need a progression through the cell cycle for their effects to work. In the case of CP506, we have done some experiments that show that CP506 induces a G2 arrest phase. So the cell cycle remains stuck there. And in this G2 phase, the DNA damage can be repaired by homologous recombination, for example, which is only active in G2 in the S phase. So that is what we observed.
Okay, but I will challenge you further. Because we are going back into also chapter 6, and it is actually connected. Because you actually try to combine it with radiation, and I love the combination, because I think you actually, the very hypoxic cells are very radioresistant, and we know that. So I would love the idea that something kills this, and then you have the radiation to kill the normoxic cells. But then what will happen in terms of the combination and in terms of the timing? So you actually want to kill first the very hypoxic cells to prevent the radioresistance arising from them, and then hit with radiation. But do you actually kill them? Because also they will be radiation protected. And could it be that the effect that you see in the figure 1 in the chapter 6 is actually coming from the diffusion to areas where cells are actually cycling and you are actually more effectively killing them?
That's again a very interesting question, and that might indeed be the case. Yeah. What we do, of course, see an effect, and CP506, the bystander effect. Well, we've shown it in the past, so it will diffuse, of course, out, and it will kill the more adjacent cells. Yeah. Maybe a way to look at that is to take, for example, a tumor cross-section and try to see if we can find any types of DNA damage that is being induced, also in the, let's say, the cells that are surrounding the necrotic core that are very anoxic or hypoxic. We can see that as well. We're recently also developing a novel approach, which is an MS approach, in which we try to identify direct adducts formed by CP506. So the cross-linked adducts in the cell itself, we can visualize that. We plan to visualize that on a whole tumor section. So in that way, you can look at where the cells in the tumor histology-wise are. Mm-hmm. If they are, for example, hypoxic, anoxic, and to see where the DNA damage is indeed being accumulated. So that might be an interesting way to investigate this.
I think that will be very crucial if you try to incorporate these aspects into a clinical, prospective clinical trial, Because I can easily argue that then eliminating the hypoxic cells at the beginning has a lot of benefits, but if you are not actually killing them, they might be still the root of the relapse in the tumor. So then you might think of a hypofractionation to really also reduce the levels of the normoxic cells and then hit them into the second row in the meantime with the CP506 or even at the end of radiotherapy. I mean, right now I can easily see benefits from both sides.
Yeah, that is why we also try to investigate a bit both sides, because they each have their pros and cons. So it's very likely. And also you can combine it with other treatment strategies to increase further oxygen consumption, perhaps even, I don't know. It's very interesting what we can all do. It's very unlikely that only 2 drugs or maybe one drug not at all, but that a combination of 2 drugs is going to be effective for all cancer types. So it's very interesting to explore different kind of options that focus on this root of the problem.
Thank you very much. I return to the director.
Thank you very much, Dr. Menegakis. And we continue the opposition with Dr. Maschke he is the senior scientist, cell biology at the University of Essen. Dr. Maschke.
Thank you very much, Prorector. Thank you, candidate, for a nice talk, and I can only say again that it's a great piece of work you put together here. I was impressed by that. A lot of question has already been asked, so I am like the last one. What to ask else? I mean, probably starting from your general idea of a prodrug, how it is working, right? You need absence of oxygen, right, that it activated, and it works best if you have an HR defect. So what do you think? Would activation of oxygen consumption also result in lower oxygen levels and thereby help to induce hypoxia, that the prodrug gets activated and work better? Would it be sufficient? So what are your idea on this? And because there are a lot of high OXPHOS tumors around also, right?
Yeah. Esteemed opponent, thank you for your nice words and your question. So if I understand it correctly, is if we can increase the oxygen consumption to increase the degree of tumor hypoxia. Yes. I think that's a strategy that has already been investigated as well by use of certain drugs that try to boost this metabolism. To be honest, I'm not completely aware of the findings of this, but in theory that could of course lead to an increased oxygen consumption, less oxygen being present and more hypoxia. If that would be sufficient to increase the hypoxic zones that are truly severely hypoxic enough for CP506 to become activated, that I'm not sure of, because you truly need a very low amount of oxygen, and otherwise CP506 will not be activated at all. Okay. So likely it can improve, if given, it can improve maybe the tumor decrease the tumor oxygenation, improve the hypoxic fraction slightly, but that will depend on the tumor hypoxic fraction already being present and the severity of that.
Okay. If we now think on tumor metabolism, which is also changed by hypoxia, for example, I mean, could you imagine a situation that you could also metabolically induce HRness, and would it be helpful for your cells, for your treatment strategy you propose?
So metabolically induce HR deficiency?
Yeah.
I think that studies are being done to try to identify inhibitors of HR, so pharmacologically. They are not being applied into the clinic. So we have different inhibitors of DNA repair that are currently also being used, PARP inhibitors, for example, and other kind of drugs. But I think specific inhibitors of HR are not currently on the market to be used. I think that there are a bit of experimental drugs. For example, you have the D-bait that is being investigated in a group. There's small parts of DNA that act as a decoy, so that the DNA repair enzymes are being decoyed and do not repair the DNA damage. That might result in a slight inhibition non-specifically of homologous recombination repair. So yeah, I think it's a very interesting option to approach, and I hope that these drugs will remain in investigation and can lead to a approved agent, because it will not only aid in improving the efficacy of CP506, but basically any other drug or therapy that induces double-strand DNA breaks and relies on HR for the repair.
Do you think that you need, for sure you need the absence of oxygen, but let's imagine you will stabilize HIF only and induce something like pseudo-hypoxia, would your drug will be working?
If HIF only is activated?
Yeah.
No, because it truly needs molecular oxygen to act as an electron donor to reduce the CP5 of oxygenate it back to the prodrug. Yeah.
And are you aware of the oncometabolite 2-hydroxyglutarate? Which is induced by severe acute hypoxia? Chronic hypoxia?
Unfortunately not, but I am now.
This was shown by Sulkowski and Glaser group also to induce homologous combination repair defect within the cell lines. When this basically can also be induced under normoxic conditions. So what I was trying to ask is whether it would be also as an interesting strategy not to focus only on HR deficiency from a genetic point of view, but probably try to induce HR deficiency by metabolic modulation to make your treatment available for more patients, right? More patient cohorts. But great, thank you. I still have time, that's good. Let's see. The other question is probably on the explanation of or use of flash therapy. You mentioned that in chapter 2, that it spares normal tissue. How does flash, do you think, minimize the effects on DNA damage?
Flash results, I think flash results is a very high dose of a radiotherapy, which more than 40 gray per second. So that's of course much more than a conventional radiotherapy. And in this way, one of the hypotheses that it reduces the DNA damage is by the oxygen consumption hypothesis. So because of the high dose of radiotherapy, of the radiation being given, the oxygen is locally being depleted, which results in then a less sensitive phenotype for the radiation therapy. Because radiation, it induces direct DNA breaks, but it can also induce, it's ionizing radiation, molecules that can react with DNA or other macromolecules. If oxygen is present, this is fixing the damage. By the flash, it depletes the oxygen, so the damage is not immediately fixed. And the idea is that the repair of the damage, of the indirect damage, is faster than the reoxygenation after the flash. That is one of the hypotheses.
Good. In this regards, I think you mentioned that you induce something like normal tissue protection by making them, so to say, hypoxic by depletion of oxygen, right? This is in your thesis. So then, would your CP506 also damage in this regard the normal tissue because it's then activated, right?
If there is no molecular oxygen present, not at all, then it might very well be the case that you get subsequent reduction, no oxygen is present, and progression to the formation of the activated metabolites.
Is it a good idea to use flash plus CP506 in regard of normal tissue protection? Or?
I wouldn't say so. Of course, it's the timing that is very important. Sure. So when does reoxygenation take place after the flash? But immediately after, when you induce hypoxia or severe hypoxia, then I would not give CP506.
Could you think of now going to the clinic? I mean, tumors find always ways to get resistant. Can you imagine any resistant mechanism to your drug or your treatment strategy?
Potential resistant mechanisms could be, you have a lot of drug transporters, for example, that are being upregulated and confer or lead to resistance to chemotherapeutic agents. That might be a reason for CP506, or cells to become less sensitive to CP506. Then again, CP506 is a drug with a potent bystander effect, so that might bypass that slightly. But it might be that the cells become more resistant using that mechanism.
Okay, that's good. What else? Now I lost my thought. Probably on the PET. I'm not a PET expert, but do you think the resolution of your tracer you suggest here, FHX4, is enough to predict and also dynamically monitor the tumor hypoxic areas? Because you want to use it as a marker, right, as a biomarker.
Yes, so when I was writing this chapter, I was really convinced that this was the best way to image tumor hypoxia. But now I'm not. I think that there are several other better methods to do that. For example, San Giuliano published a paper that was based on hypoxia PET imaging, but that built a CT radiomic signature based on that. That is a non-invasive way that can be performed at multiple time points, so you do not have the metabolism of HX4 that needs to be accounted for. So I think that is just a better option to do it that way. Yeah. So I would personally not use HX4 in this regard.
And probably we're almost there. So there's no value in anything. Okay.
So I'm afraid we have to stop here. Thank you for all the questions and filling up the time. Alexander van der Wiel, de gelegenheid voor het verdedigen van uw proefschrift is voorbij. De promotiecommissie zal zich nu voor beraad terugtrekken. En ik verzoek u en uw gezelschap om onze terugkeer en de uitslag van dit beraad in deze zaal af te wachten.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Long road to the south side. 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. All your time, 'cause I'll go the extra mile. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Hit the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. Even though these nights seem long, I know that I am never on my own. Know you've won the battle once you've grown. South side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. your mind. Years can't fly by now, don't waste all your time. 'Cause I'll go the extra mile.
dokter wordt of niet.
Alexander van der Wiel. De commissie hier aanwezig heeft zich beraden over de kwaliteit van uw proefschrift en de wijze waarop u het proefschrift heeft verdedigd. Op grond van haar positief oordeel en gelet op de examens die u vroeger heeft afgelegd, heeft zij besloten u het gevraagde doctoraat toe te kennen. De hoogleraar professor Lambin is gemachtigd u op de gebruikelijke wijze met deze waardigheid te bekleden. Het woord is nou aan uw promotor.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent and responsible?
I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Alexander Marie-Madeleine Adrianus van der Wiel, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with the degree certificates signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university. I will give now the words to your supervisors, Luduc Dubois.
Beste dokter van der Wiel. Na 5 jaar. Beste Alex. Gefeliciteerd met het behalen van je PhD. Ook in naam van Philippe Ala en de Hans afdeling. Bij deze wil ik ook mijn felicitaties uitdrukken naar je ouders, familie en vrienden. Jij stond hier een uur in het middelpunt van de belangstelling. So, before I continue, I would first like to thank all members of the reading committee and the opposition for their efforts reading your thesis and preparing questions for you. It's really highly appreciated. But back to you. Terug naar jou, Alex. Wel, eigenlijk niet naar jou, maar over jou. Ik wil je familie en vrienden even meenemen naar hoe het leven van Alex er in het lab uitziet. Eerst naar hoe het begon. Na heel wat omzwervingen van Neerpelt, of moet ik nu Pelt zeggen, naar Hasselt, Maastricht en Kyoto, kwam je terug naar Maastricht om je te melden bij ons voor een PhD-positie. Dat was wel snel beklonken, want we waren toen al onder de indruk van jouw presentatieskills, net zoals we vandaag ook gezien hebben. Jij nam de fakkel over van Rijmen en werkte verder aan het CP506-verhaal. Nu, hoe werkte Alex nu in het lab? Alex zijn dag op het lab begon altijd met een koffie. Nee, ik ben verkeerd. Vooraleer Alex op het werk kwam, had hij waarschijnlijk al een handse kop koffie op. Waarschijnlijk gebruikte hij dit als een energiedrankje of zo, want je moet weten, Alex is heel sportief. Hij komt namelijk altijd met de fiets naar het werk. Maar vaak moest ik toch even naar buiten kijken, want Alex kwam vaak zo bezweet toe dat ik me afvroeg of dat het nu eigenlijk regende of niet. Dus dan toch maar eerst nog een koffietje nemen om even te bekomen. Dit is ook de reden waarom Alex vaak meestal enkele minuten later toekwam op een werkbespreking. Ja, tuurlijk, die koffie moest eerst genomen worden. Nu, in het lab stond alles in het teken van CP506. Of er nu experimenten in het lab zelf waren, of in de proefdierfaciliteit. Alex was altijd heel behulpzaam toe. Naar andere mensen en naar andere mensen hun onderzoek. Nu, dat is ook zichtbaar in zijn publicatielijst. 7 papers gepubliceerd, eentje onder revisie en 2 in voorbereiding. Wacht, ik vergeet even nog te vermelden dat we ondertussen 5 kopjes koffie verder zijn. Alex had eigenlijk leerkracht moeten worden. Of misschien had hij leerkracht moeten worden. Want hij heeft verschillende keren geholpen met een PET-practicum. Ook al was dit online, omwille van corona. Maar nu het voordeel van online lesgeven is dat je natuurlijk veel koffie kunt drinken. Je was ook een heel goede mentor in het lab. Vraag maar aan je laatste student Leslie. Die heeft nu zelfs de fakkel van jou overgenomen en is bezig met haar PhD op CP506. Nu, de grootste verwezenlijking van Alex tijdens zijn PhD-traject was niet de koffie, maar was de eerste publicatie van CP506. Dat heeft echt heel lang geduurd. Eerst de verschillende versies met Auckland, daarna de verschillende journals. Ik ben echt de tel kwijtgeraakt hoeveel journals we eigenlijk gehad hebben vooraleer dat het verhaal geaccepteerd was. Maar het is je gelukt. Dus mijn oprechte dank voor jouw doorzettingsvermogen. Nu, gelukkig dat deze versies in Word waren getypt. Nu kan Alex de afkorting dokter gebruiken, of DR gebruiken. Dokter met een O. Maar soms denk ik dat Alex stiekem ook dokter met een E wilde worden. Waarom? Wel, dokters hebben vaak een handschrift die onleesbaar is. Alex ook. Zijn handschrift is gewoon tout court onleesbaar. Niet alleen voor ons, maar ook voor hemzelf. We hebben reeds enkele maanden plezier aan het ontcijferen van je handschrift op aluminiumpotjes. En ik denk dat we nog enkele maanden werk zullen hebben om dat werk af te ronden. Dus hierbij wil je mij alsjeblieft die laatste file even doorsturen? Dank u. Nu, je bent ondertussen gestart met je opleiding klinisch chemicus in Eindhoven. En mogelijk ligt die oorsprong van die beslissing in Japan, aangezien je daar een masterthesis hebt gedaan op de afdeling scheikunde. Een tweede bewijs hiervoor hebben jullie kunnen zien tijdens de presentatie, want Alex kon het toch niet laten om enkele chemische formules te tonen. In ieder geval, ik hoop dat ze daar goede koffie hebben. Want voor ons zal het de komende jaren in ieder geval financieel een heel stuk goedkoper worden. Nogmaals proficiat en wij wensen jou veel succes en geluk in Eindhoven.
Dank je wel.
Dr. van der Wiel, namens de Universiteit van Maastricht mag ik u ook feliciteren met uw behaalde dokterstitel. En uiteraard wil ik ook uw promotieteam daarbij betrekken. Want zonder hun was het ook allemaal niet voor elkaar gekomen. En uiteraard ook uw ouders, broers, partner. Die allemaal toch op de achtergrond een bijdrage hebben geleverd. And also a very great thank you to the people from outside Canada, Switzerland, but now in India, and also from Germany. The university is very grateful for that you were involved in this promotion. So thank you again. Well, we will end the session here. Dus ik sluit hierbij de academische zitting. Voordat ik eerst nog uitleg dat we gaan een foto maken met het promotieteam, met de gasten op de achtergrond op het scherm. En daarna komt er nog een statiefoto op de trap. En ik begrijp dat de receptie elders plaatsvindt. Hierbij sluit ik deze academische zitting.
Dankjewel.
Mooi gedaan.
Dankjewel.
Ik weet niet of iemand een foto maakt. Heb je iemand bedacht?
Ja, mijn moeder hier eigenlijk. Ja.